Good morning. This is being recorded on Sunday morning instead of Saturday morning as usual. I kind of had something come up yesterday, so I wasn't able to make the video, but I'm making it now, and hopefully you guys have enough time to watch it before class tomorrow. Just looking at analytics, seems like most people watch them on Sundays anyways, and usually I try to give people a little bit more leeway, but today, or before class on Monday, so folks do that as well. So anyway, let's go ahead and start talking about logarithms, which is the main plan for this video. So the last video was about exponentials, and we looked at exponent properties, and today we're going to look at logarithms and logarithm properties. Okay, so learning objectives for this lesson are to first state the definition of what a logarithm is, determine the domain and range for a logarithm. So like when you're trying to compute logarithms with a calculator, what numbers can you actually take logs of? What can't you take logs of? What are the answers you're going to get out? And then to prove some logarithm properties from exponential properties, because it turns out logarithms and exponentials, they are best pals, they're best buddies, they go together because they are inverse functions for each other. Okay, so to start off, we need to understand a little bit more about exponential functions. I've kind of briefly talked about exponential functions, and you've computed a table of values for exponential functions. We're going to just look at the simple one, 2 to the x. It's like the doubling function. You know, each time x increases, you multiply by another 2. So our table of values for 2 to the x looks something like this. You know, if you put -3 in, you get 1/8 out. And the reason why you get 1/8 is because, you know, 2 to the -3 is, and -2 you get a quarter, -1, a half. You know, each time you go up by 1 here, plus 1, you're going to go times by 2 over here. So you're going to double it every time you go up by 1 with the left column. And from this, you should be able to interpret a pattern and interpret what will happen if you were to keep going. So if you kept going down with the x's, you should end up getting larger and larger values. Right? The next one's going to be 16, which is twice what 8 was. The next one's going to be 32 and 64 and so forth. And so there's no limit to the size of the answers as x gets bigger and bigger. So you'll find that this number just keeps getting larger and larger. And then what happens in the other direction? Well, in the other direction, these numbers keep getting halved. So if we go backwards 1/8, we're going to get 1/16. That's half of an eighth. And then we're going to get 1/32. And we're going to get smaller and smaller numbers. But they're always going to stay positive, and they're just going to be above that x-axis. You're going to hover along that x-axis, getting closer and closer to it as you go further to the left. So we're going to go close to 0 as we go to the left, and go up to infinity as we go to the right. So you get a graph that looks something like this. You know, that's a snapshot of it. You'll notice that it has an asymptote. We've got a horizontal asymptote here, and that's y equals to 0. Horizontal asymptote at 0. And there's no vertical asymptote. It just is defined for any x. You can plug any number into this thing, and it's going to get you some positive number out. So from this, we should be able to determine the domain and the range. So for that function, our domain is going to be all real numbers. We can plug anything into 2 to the x, even a weird fraction, even something that's, you know, like 2 to the pi. You can actually compute 2 to the pi to some number of decimal places with the calculator. You know, what does that actually mean? It's really hard to understand what 2 times itself pi times is, but you can kind of think about, well, it's 2 times itself 3 times plus a little bit extra. So yeah, you can kind of work your way there, you know, to what the answer would be with decimal values. The range is going to be all positive numbers, so you can get any positive answer out. You can't get 0. That's a key piece, is that you can't actually get 0, and you're not going to be able to get a negative number from 2 to the x. It's only going to give you a positive answer. Okay, so again, some justification why this is. Well, just evaluate it with the calculator. If you plug in 2 to the negative 100, that's 1 divided by 2 to the 100 power. You have 1 over a tremendously large number. So 1 divided by something huge is very, very small. This notation may be familiar for some of you, may not be. 7.9 times 10 to the negative 31, that says to put 31 zeros. Excuse me. Yeah. So that's 31 zeros. I'm not going to write them all out, but there's going to be a lot of zeros and then 7, 9. Okay, so actually I believe it's 30 zeros. Anyway, so it's a decimal place, a whole bunch of zeros, and then 7, 9. So that's a really, really small positive number, and that's important. It's positive, it's not 0, it's not negative. It will stay above that x-axis. If you plug in 2 to the 100 power, now you're going to get a tremendously large number. It's going to be a number so big that your calculator can't display it all. Typically, it has to use this, again, scientific notation to display this number because there's so many zeros following it, right? It's a number with a tremendous number of decimal places. It's 30 decimal places long. So, 1.127, and then it keeps going for a long ways, okay? So, again, large positive number. So we're going to be able to get anything out, any positive number out. We cannot get anything negative. We cannot get 0, no matter how hard we try with 2 to the x. Now, why all the hubbub about this function about 2 to the x and its domain and range? Well, we want to determine if it's invertible, if we can come up with an inverse function. Is it 1 to 1? If it's 1 to 1, it's going to have an inverse, and we're going to be able to, use this inverse function for reversing exponentials. From its graph, it looks 1 to 1. You can just draw on these horizontal lines, and you can, test out. Oh yeah, it seems to only hit it once. Earlier we learned that every increasing function is 1 to 1 as well. Is 2 to the x increasing? That means as you go right, does it go up a little bit? And the answer to that question is also yes. It's increasing, so that means that whenever we have an input that's a little bit to the right, or as far to the right as we want, from another input, the value at the further to the right input, so the value at 2, so this is 2 to the b, so if b is bigger than a, so if we're to the right of a, then the value 2 to the b is more than the value 2 to the a. So, you can a over here, you can choose a b over here, and what that's telling you is that f of a here is smaller or lower than f of b. F of b is above f of a when b is to the right of a. And the answer to that is yes. Again, we can inspect the graph to kind of understand why this is true. Even if you go really far to the left, if you go to the right, you'll be a little bit higher. Now, to really prove why this is true, you kind of need to delve into the realms of calculus. But for now, we can just kind of assume that it is an increasing function. That means as you go right, you go up. Because it's increasing, it's going to be 1 to 1. Is it always increasing? Well, I'm talking about 2 to the x right now. Is b to the x always an increasing function? And the answer to that is no. It doesn't have to be an increasing function. It can be a decreasing function. And it's decreasing if b, that base of our exponential, is between 0 and 1. So if the base is, for example, 1/2, if we were to do 1/2 to the x power, then it would be kind of the flip of this graph. Let me go ahead and erase all this on this. If we were to graph 1/2 to the x, you'd find that it is a strictly decreasing function. I'm going to graph it in green so it looks a little bit different. And it's going to look something like this. that would be 1/2 to the x power. And it's actually symmetric about the y-axis for this one. And then you would notice that if you go right, you actually go down. So that happens when that base is between 0 and 1. You're going to end up with what's commonly referred to as exponential decay, whereas with this 1, 2 to the x, you have exponential growth, where it keeps getting bigger and bigger instead of getting smaller and smaller as you go right. Okay, so we've determined that it's 1 to 1. That means it's going to have an inverse function. And so what is the inverse function called? Well, it's called a logarithm. We call inverses to exponentials logarithms, just like we call inverses to square roots, or to squares, square roots. So squaring and square rooting are inverses of each other. Exponentials and logarithms are inverses of each other. The notation we are going to use for a logarithm looks like this. You say log the base of the exponential function you're inverting, and then x, log base 2 of x. This is how you'd say this. You would say this as log of x, pronouncing that function right there. And so you could have log base 3 of x, log base 10 of x, just depending on whatever b is. The domain and range of this function, log base 2 of x, will be the reverse of the domain and range of 2 to the x. So remember, 2 to the x was all real numbers as its domain and positives as the range. That means for logarithms, its domain is positives and its range is going to be all reals. So that means that you can only put a positive number into a logarithm, and you can get any number out. So a logarithm is going to have a range of all real numbers, and it's a domain of only positives. Okay? So here's a table of values for what the logarithm looks like. I'm going to go and erase this. So logarithms table of values. Remember, to find the table of values of an inverse, you just simply flip the columns from one another. That gets you the table for the inverse function. If you put 1/8 into log base 2, you get -3. If you put 1/4 into log base 2, you get -2. If you put 1/2, you get -1. You put 1, you get 0, 2, and 1, 4, 2, 8, 3. Log base 2 is telling you what exponent you need to raise 2 to so that you get the thing on the left, whatever is your x, right? What exponent do you need to raise 2 to so that you get? So its graph, it's going to look something like this. You know, for 2 to the x, you've got the red graph here. We draw on the line y equals x, and that's the line of reflection to draw our inverse function, right? We swap x and y values. So our inverse is going to be over here. This is the blue function, log base 2 of x. So you can see these points on this graph over here. You know, they're a little bit hard to find, but we can try to find them. So like 1/8 -3, it's going to be right here. And then 1/4 -2, that's going to be right there, just a little bit above it. 1/2 -1, 1, 0 is right there. 2, 1, 4, 2, 8, 3, and so forth. You can see those values, those points on this graph. I'm not going to go into the desmos of it too much. Just one thing to note: the logarithm has a vertical asymptote. So we have a vertical asymptote for the logarithm at x equals 0. X equals 0 is our vertical asymptote. The previous function, or the inverse, 2 to the x, had a horizontal asymptote. So the logarithm, its inverse, is going to have a vertical asymptote. So those horizontal asymptotes switched to vertical asymptotes when you take these. They get reflected across the line y equals x as well. Okay, so that's our logarithm function. Now we're going to go ahead and look at some logarithm properties. And namely, let's first get into another way to frame the logarithm. Again, it's going to be in terms of exponentials. So, definition. Suppose we have a positive number for b, and x is any real number. So x can be negative, positive, irrational, rational, anything you want it to be. Then we have this relationship. B to the x equals y if and only if the log base b of y equals x. So this is the kind of golden rule of what a logarithm means. Logarithms are giving you the exponent. A logarithm gives you the exponent. A log is an exponent. It's the exponent that you would raise b to so that you would get whatever's inside the logarithm. So this is very similar to square roots and squaring, okay? And so you may have seen squares and square roots compared in this similar way. I'm going to go ahead and write down the analogous statement to this for squares and square roots. So if we were to have x squared equal to y, so x squared, you know, x is some number, positive, negative, 0, it can be anything. And when we square it, you get y. An analogous statement would be that the square root of y to x, okay? So then tell you how to kind of go back and forth. So you can, for example, you know, if y is equal to 4, then square root of 4 would be 2, because 2 is the number squared that you get 4, right? And from this we can see there's nice numbers to plug into y. You know that there's very nice numbers to plug into y, such as 1, 4, 16, 25, all those perfect squares. Similarly, there will be nice numbers to plug into a logarithm. And the nice numbers to plug into a logarithm are powers of the base b. So powers of b will be nice numbers to plug in that get you a couple of notation things as well. If you write a logarithm with no base, with b omitted, then that really means the log base 10. So you'll see on your calculators, if you have a calculator nearby, or next time you look at it, you'll see a log button on there, and that really means log base 10. And if you see the ln is another common logarithm to take, and that's log base e. Remember e, the famous exponential base, the one that we use for continuously compounding interest. That logarithm, the base for that is natural log. This is also called the natural log. The natural, whereas, and that's what ln, log natural, I don't know, it's probably French why it's in that order. But the log without a base is log base 10. And then ln just means log base e, or natural log. Okay, so an example of using this relationship between exponentials and logarithms. 2 cubed equals 8. There's a statement that looks like the statement on the left. 2 to the third power equals 8. If we take those three numbers, b, x, and y, and rearrange them in logarithm form, what this means is that log base 2 of 8 equals 3. So the logarithm base 2 of the number 8 is going to be what you raise 2 to equal 8. And then the answer to that is 3. So I'm just going to try to highlight each of these things getting placed. So this b is the base for the logarithm and the base for the exponential. And then x is the exponent, and it's what the logarithm equals, okay? The logarithm equals the exponent. Y is the result of b to the x. It's the answer to the exponential, and that's what goes inside the logarithm. So inside the logarithm, you take the answer, b to the x, and it gives you x out. So another way to think about this is that if you were to rewrite 8 using powers of 2, if you were to rewrite 8 as 2 to some power, then you would rewrite it as 2 cubed. And now it's even easier to see what the logarithm is doing. So it's even easier to see what the logarithm is doing here. The logarithm is undoing the exponential. It's undoing it and giving you whatever's in the exponent out. And the key is that these bases are equal. If those bases are not equal, then you're not going to get the exponent out. You'll have something else will happen. We'll talk about what happens when the bases are different. There's a whole change of base formula that kind of pops out from this. But suffice it to say, log base 2 of 2 cubed undoes that exponentially stuff and gives you what the exponent is. Okay? So the logarithm is a tool for undoing exponentials. Alright, so since a logarithm is related to an exponential, we're going to have a whole bunch of logarithm properties, just like we had exponential properties. And if you really keep it in the back of your head, the fact that logs are exponents, logs are this fact while you go through these, they'll make a little bit more sense. They'll be easier to remember these logarithm properties. Deriving them is a little tricky. I'm going to walk you through 1 or 2 derivations and have you do one on your own. But it's not impossible to follow, and it does hopefully give you a little bit more understanding as to why these log properties, why they're rooted in the exponential properties. Okay, so I'm going to go ahead and just start diving into what these log properties look like. So we're going to start off with A and B, capital A and B being positive real numbers. X is our base. It needs to be a, X can be any positive number, and little a and little b. So our exponent property on the left is a familiar one where you multiply 2 exponentials and you end up adding the exponents together. The logarithm property that corresponds to this is that you were to take a product, a times b, and take the log of that. You could take the log of a and the log of b and add those results together. So you should see some similarities here. You know, a similarity that we have a sum over here. This is a sum. We have a product. We have a product on the inside of the logarithm. Okay? So that's our first logarithm property, where you take a product and the log of that, you can pull it out into a sum of 2 logs. Or if you have a sum of 2 logarithms with the same base, you can smush them together into a single logarithm. Okay, the next exponential logarithm property is that if you have a quotient, log of a over b, that's equal to a difference, log of a minus log of b. So log of a quotient becomes a difference of logs. And the corresponding exponential property is that if you have a quotient of exponentials, then you can rewrite that as a single exponential with a difference of the 2 exponents. So x to the a over x to the b is x to the a minus b. Okay, the next logarithm property is if you have the log of an exponential, so log of a to the c, where c is any power, can be any real number, then you can rewrite that as c times the logarithm of a. So you can take that exponent down and put it in front. And now, this is actually very important that we can do this. And I wrote these all with base 10. So these are all in base 10. But they can be in any base. So it doesn't actually matter which base that you use for these. And so a to the c is something base capital A, which means that we can use a logarithm base 10 to get at that exponent in this case as well. So we can use log base 10 to get the exponent, even if it's not base 10. And so that's one reason why your calculators actually only have 2 log buttons. They only have the natural log and the log base 10, because you actually don't need to have any other logarithms. You don't need any other bases. It suffices to only have 1 log. In fact, the calculator doesn't need base 10 and base e. They just have both because sometimes it's nice to work in base 10, sometimes it's nice to use the natural log. But you can use a log of any base to get the exponent down. Okay? And this third property is going to motivate change of base in the next lesson. And then the last logarithm property is that if you take the log of 1, you get 0. And this is very similar to the 0 exponent property. It's our log of 1 property. X to the 0 equals 1 is analogous to log of 1 equals 0, right? This is the exponent. And that's true for any base. Okay, so these are all of our logarithm properties. I'm thinking this video is probably long enough, so what I'll do is we'll just use these properties, and then we'll have a whole video devoted to doing, working through their derivations. So how do you actually get these logarithm properties from the exponent properties for you guys to watch on Monday. So this should be enough for now, and we'll dive into kind of deriving these properties and using them in class Monday and Tuesday. And then we'll close out the week before the break, and yeah, it'll be great. So anyway, I will see you guys on Monday.